Hello, everyone. Welcome to my presentation. My name is Yuxi Hong. I'm a PhD student from KAUST. My topic is high-performance seismic redetermining on AC64FX. These are the co-authors, Mathieu, David, and Hatton. And so what is this presentation about? So we leverage low-rank matrix computation to accelerate large seismic redetermining applications. We achieve an average of 2.6 acceleration compared to dense NVM, and we scored around 9.5 terabytes, around 78 sustainable bandwidth using 16 Fujitsu A64FX1000 nodes. So let me give some seismic redetermining background. It is an important technique to get insight into the Earth's subsurface. So this requires solving an inverse problem. Traditionally, this only applied to the adjoint operation due to the computational challenge. Some latest research showed an alternative method to improve the solution using the conjugate gradient method. But this comes at the cost of some expensive matrix vector multiplication operations. So the below two equation are the inside the iterative solver, and the bar below is describe how the time is spent during each iteration. So you see that the two operations R operation is it is matrix vector multiplication. It is most time consuming one. So what we do is that we use Taylor rank matrix vector multiplication, to also known as TRI-NVM, to mitigate the complexity bottleneck. So what do we do? First, we divide the matrix into several blocks, and we use the SVD and to get and a threshold to get a part of the U base and V base. And we first multiply the V base by the X, and then we shuffle the result of phase 1 to YU, and then we multiply U bases to YU. So let's look at some data set. So the data set we use is it has 150 matrix, and the workload is 150 matrix vector multiplication. The size is 10K by 10K for each, and each matrix corresponds to information from a single frequency. So if you look at on the left, so the frequency at 33 hertz and the index is 100, it is clearly a low rank feature, and the off diagonal is sparse. So on the right, you can see the rank distribution of tiles, and the most matrix ranks are below the critical threshold. If you can, this red line is 128 and is half of our tile size and 256. So, and we test on the different frequency matrix. And on the bottom net, you can see the rank summation is larger as the matrix frequency index increase. Okay. So further, we designed two load balancing optimization techniques to mitigate the load imbalancing problem. The first is phase merge strategy. If you use naive implementation of the TRI-NVM directly onto 150 frequency matrix, and you will find that if you use static scheduling of the OpenMP, then because of the rank is different of inside each matrix, so you will see that it will have load imbalancing between the thread. So what we do is that we merge the phase of each frequency. For example, we do phase 1 of all the frequency at first, and then we open the dynamic scheduling of the OpenMP. Then it will mitigate the load imbalancing problem. Then we move to the phase 2 and the phase 3. The second is zigzag mapping strategy. So we use one MPI to map to the one core memory group. And if you use the static naive trunk allocation, which means that the first MPI is responsible for the first partition, partition of the dataset, but it will cause the problem that it has less work than the last MPI process, right? So what we do is that we use this zigzag mapping strategy. We try to allocate the workload evenly to all the MPI process. Then let's look at some approximation result of TRI-NVM using different error threshold. And BCD is the approximated result of the TRI-NVM with different error threshold. E is the compression error of the B with A. And then it is very negligible error to the final image. So we multiply by 10 and we multiply the same thing of G at H of C and D. So you can see that with error threshold equals to 1 minus 3, it is very negligible. There is a very negligible error in the final image. And so this is application SNR with different algorithm configurations. So there are two parameters for user to tune the algorithm to trade off the flop saving and the application accuracy. For example, the error threshold and tile size. And we use SNR, signal to noise ratio, to quantify the quality, and we test on different tile size and accuracy threshold. In the left figure, from left to right, the error threshold is 1 minus 3, and 5 minus 3, and 1 minus 3. And we set 40 as SNR threshold. We finally get two eligible configuration. We conduct a subsequent experiment using MB equals to 256 and error accuracy equals to 1 minus 3. On the left, it is a flop saving heat map. And you can see, let's check the time analysis of each single frequency matrix. The red one is a dense NVM, and the blue one is the TR NVM. And on the left, it is on the right, it is a bandwidth. And we see that higher frequency takes more time to process. And for each single frequency, we are better than the dense NVM. So for the dense NVM, we use scalability, parallel NVM, and map each MPI process to the one core memory group. And let's look at the single node TR NVM performance. Since the 150 frequency matrix is too large to fit inside the 32 gigabytes memory, so we split our data set into two parts. So the first part, the first half, so this is a time and bandwidth result, and we use four type of TR NVM, which enable merge phase or enable the zigzag mapping, or both enabled. And we try to compare it with the dense NVM. So the best one, which both optimization is on, gave us 6.3 accelerations, while in the second half, so the best one gave us 2.4 accelerations. So yeah, and let's look at how we enhance the data locality with the core memory group aware mapping. So if you remember previously, so we map one MPI process to one core memory group, but we have 16 nodes in total. When the input matrices cannot be evenly distributed across the node, it may lower the performance. So if you look at the right two figure, so the first experiment is the 16 node with 128 frequency. And as you can see, if you use one MPI if you use one core memory group per MPI process, and you will get the best performance. But if you your input is from 150 frequency, and if you're still using your one core memory group per MPI process, you will have immediately have much lower performance. So what we do is that we try to set a dynamic scheme that you can configure your core memory group per MPI process, for example, 2. And then we try the 1, 2, 4, 8, 4 type of configuration. And then we find that two core memory groups per MPI process give us best performance. So let's finally look at the performance scalability result. And we have seen this two figures at the beginning, and we reached the main idea we want to convey is that we reached 2.7 acceleration, and we also obtained the 78 sustainable bandwidth using 16 Fujitsu A64FX1000 nodes. Thank you so much. This is my presentation. We thank Fujitsu Corporation for remote hardware access.